So, not taking your time much as it is our last day, and hope we will meet many times by conducting new workshops and courses, short-term courses, FTP in future also. So, Basu, can you please share the slides and give the brief introduction about the things what we are working on in our Adit lab,
Yes, sir.
please?
Okay. Thank you, sir, for
And
your.
Basu, after that, we can have a small quiz that
Hmm.
we have prepared to the
Um,
participants. Please share these questions to them, and
hmm.
then as feedback, and then we can close this. Okay?
Yeah, we can say we will
Yeah.
share the quiz link in 8 p.m. maybe, sir, after this lecture, 1 hour
Sure,
lecture, and then yeah.
sure, sure. Please.
Okay. I think it is visible. The screen is visible, right?
Yes, yes.
Okay. Yeah. Thank you, Dr. Arnab Sukla, sir, for your introducing me. And today I will be giving some experience or experience and that I have learned from my research that will be based on the my observations and the whatever facilities that we have in our lab. I have explored and have some experience. Based on that, the topic will be here: hardware in the loop test bed for cyber physical systems for unlocking new possibilities. So, as Dr. Anup Sukla sir has told that my name is Karamdao Basumotari. I'm a PhD scholar working on the cyber physical systems of our systems. Yeah. Before going into the main presentations, I would like to highlight the presentations flow. First, I would like to highlight the new trends or paradigm shift of the power systems and the why cyber physical system testbed is important and testbed and the hardware available that we have in IIT Jammu at Adrid Lab and some examples. I would like to discuss some examples, like 5 examples that we are working on the cyber physical systems. Another maybe we are working also with the digital twin reference model, and I have some experience in the transmission system modeling in PSCC as well, which I would like to share experience. Yeah, that is the main slide. As I have told, the paradigm shift of the four systems, what's going on as compared to the conventional grid. If we talk about the production side, compared to conventional systems, many small producers we see right now, distributed energy resources. And if we talk about the market, we see the decentralized, and there is no boundary for the bidding the the bidding the energy sources. And in terms of transmission lines, we talk more about nowadays about the microgrid, network microgrids, and including small scale transmission and regional supply compensations. If we come to the distribution sides, earlier we had this one-way one-way power flow, but we see now both directions of power flow. Consumer, earlier we had the consumers were passive, only the paying the price for the energy only, but now they are active. They are contributing, supplying their energy, and also participating in the system also. So now, on the right, that is the trends of our system evolution from the 1882 to present and future. As this Gyan course also based on the resiliency of the distributed energy power systems. So, as the during the course expert Dr. Srivastava also and some instructor also telling that about the smart grids, renewable integration, grid resilience, and cyber security, and digital twins and some artificial intelligence application in the power system. The question is why we need to develop the test bed. First, the when we talk about the test bed developing, then someone has to have to think about what's going on in my mind. So first, maybe a self-testing environment. Suppose you develop or thinking about some algorithms you would like to deploy in the field. First, before testing in the field, you might be testing in the lab. Your algorithm is feasible and how it is robust. Maybe you would like to implement a security measures in the testbed or security and vulnerability assessments. Maybe you would like to, suppose you design a systems, you would you want to identify the vulnerabilities and develop a robust cyber security solutions. Maybe the realistic simulation and validations, which maybe you have developed a test bed and you would like to test or validate the system performance before actual deployment. In the form of maybe you would like to see how much latency in between the devices sending the signals and synchronizations, maybe failure scenarios you would like to analyze. Maybe cost effective development. Suppose you would like, as a utility company, they want to test their products uh, before deployment. They would like to test it in the cyber physical test bed they have developed, because actual deployment, actual testing in the grid may be very costly or very dangerous, which is not suggestible. So for example, on the right, I have here in the cyber, I think you are able to track my cursor. So that is the cyber part. If that is the cyber means this HMI is from the real-time automation controller, where if you see here some logics that I have written here, and that is the planned process or systems, means physical part here, maybe you have some protection relays, many measurement devices, that is physical, and you might have a control systems there. And for examples, I would like to simplify it here. uh, Here is my automation controller's HMI, and there is a protection relays here, and that is the breaker, circuit breakers, which I would like to trip, and trip or close or open, right? So what happened is that suppose this relay having some data, and this data that I am taking it to the RTEC, and this RTEC is conditionally, you know, sending some signals to again back to the relay, and relay changing the breaker whether it should be on or off. So this decision is decided by these algorithms written in the RTEC. These signals getting exchange between the cyber and physical. It's possible because of the DNP, Modbus, and IEC 6150 or some other protocols. Yeah, this protocol is vulnerable as Dr. Srivastava and some other lectures. In some other lecture also you might heard about cyber perspective that is you know dangerous. And these are the hardwares available that we have in the other lab. And this one, 8, and 8 that I have highlighted here, that is the GPS antenna. And this one is the real-time synchronization clock. And this SL2240 Axion, it's a real-time automation controller which can be acting as a PDC and PMO as well. And this SL3350 also can act as a PDC and automation controller. And this one SL421, which is a transmission line protection relay, which also can acting as a PMU, phasor measurement unit. And this one here we have SL3350, that is also the real-time automation controller. And we have two feeder relay protection relay here. And this one is the RTDS backside, different cards and connections. At the front side, I will show you in the next few slides. First, when we are thinking about the testbed development, then somebody has to think in his or her mind that what I want to achieve from the testbed. For example, suppose I would like to implement the overcurrent protection. So overcurrent protection, right? I can't test it directly in the physical grid. So that's why I'm simulating it in the RTDS. Suppose this one is the distribution line feeder you have, and you have the protection relay here, and you would like to trip this breaker inside the RTDS right now. This feeder have the CT and PT installed in it, and this CT-PT signal, current or voltage signal, will be getting to the relay, SL751, let's say, and this relay will uh, send a trip command based on the current it received during the simulation, and if overcurrent limit or threshold will exceed, then this relay should trip. So this GTA or retain here is the hardware that takes the current and voltage to the relay, and our relay have the low signal interface, which can take a real voltage and current from the RTDS, and the some as I'm sorry that I forgot to mention that I'm working on the mostly focus on the IEC 6150 protocol application in my research. So I'm using IEC 6150 mostly, so I will be telling most on the IEC 61505. So this PIOC is instantaneous overcurrent protection, and this PTRC represents the protection trip conditioning. So these are the logical nodes in the ISA 62150 standard. And if I would like to trigger the relay, then I should have these logical nodes in my data sets. So this PIOC.str means start general will validate or check always whether this threshold will be exceed or not. If that will be exceeding, then it will issue a protection trip condition. It will send a condition signal to the PTRC. If this PTRC receives the signal, if it will check the breaker condition, whether it should need to open or close the breaker. According to it will do according to grid conditions, and the breaker also sends us, the open or close status back to the relay, and relay will send again to the RTDS, so that we can monitor whether the breaker is working, right way or not. And this is the modeling of the IEC 6150 in RTDS and SL751, and different tools I have used. Tools means here, suppose I'm working on the SL751 or SL protection relays and devices. So I'm using accelerator architect software in order to create a data set. And in RTDS side, there is also a IEC 6150 data model, and this side is the automation controller RTX HMI, where you can write many programs. You can get the data from the relay and RTDS again. So when I started working with the IEC 6150, I had many confusions how to start with, the first three questions that I have, learned from my experience is that when you working with a IEC 6150, then you should know where is your data. What is your data? What kind of data you want? And how to get this data into the RTDS? How to get? And if you know how to get it, now how to model the data to have from SL751 to the RTDS. So the answer would be, you have the accelerator architect software, you have the IED palette here, as different SL devices, IEDs, they have the palette here. You can, suppose you want a SL751, then you just drag and drop it to the project editor, and when you have this one, you just click it there, and if you click there, you need to configure what is the IP address of this relay, and which port or Ethernet port it is connecting. So, and as I have already mentioned, where is your data, right? So here is, there you see there is data sets at the screen. You just click it there, and I'm sorry here it's not visible here, but there is new button here. You just click it there, new. Then suppose you, as I have mentioned here, you need a PIOC, right? Instantaneous overcurrent protections logical nodes, and PTRC, protection trip conditions and breaker status. So you will take this here, overcurrent pickup PIOC and protection logical nodes PTRC and circuit breaker status. These data sets will be created in your accelerator architect software. After creating the data sets, now your relay should get the updated data, right? So you will send the CID file. CID means configure ID description file. That is the most important file when you're working with the IEC 650. You will just right click here, right click and send the CID file to the relay. Now, when you send it, then your relay will receive the updated, data sets. After, sending the data, then you need to export this same file as a CID file because you would like to have your data somewhere. Suppose, let's say here RTDS, right? As I have mentioned, RTDS has its own IEC 650 data model. So you need to create a project in RTDS, and you need to create same data sets that you have created because you need to label it in the RTDS. So accordingly, I have created here input because I'm taking it into RTDS, so input is coming, right? If I'm sending from RTDS, then you can label it output. So as I'm taking it, and I'm creating it in underscore PIOC like this. Uh, the data sets I created in the same way in the architect software, I'm creating it in my here in RTDS. Okay, and you have to import the file that you have created in your architect software. You as maybe it's not visible, but I have import here. Then when you import it, you need to bind the data because you need to have in your RTDS. So you will bind the data so the RTDS in RTDS you can monitor, you can have all this data. So here I'm binding the data. Now after completing it, you need to export the same CID file that has been created in the RTDS because you would like to have the data in the again in the relay, maybe in the RTEC. So you will export it and import it into the RTEC HMI also in RTEC also, and also in the architect software to have the updated data sending to again to relay and RTEC software. That is the testbed that we have implemented, and that is the here. That is some tools that we have used: accelerator quickset, accelerator architect software, and WireShark for sniping the data. That is the same Peter that I have mentioned earlier. And as we have a CT and PT, we are taking the voltage and current via a GTAO card, as I have mentioned, right? So in the GTAO this block, we are scaling down the signal because we are using the low level interface. So this low level interface have the signal should be very low, around 500 millivolt or milliampere. So before injecting the real voltage and current signal into the relay, you should check it whether you have determined or getting the right signal before injecting into the relay. And this relay and RTDS simulation time step it's synchronized by an external clock that SL2488. And this simulation synchronizations in the RTDS, it's done by a GT Sync card. Okay, and that is the validations. As I have mentioned that before, injecting the signal into the relay, first you need to test it, getting out from the GTO card, and the signal should be in between the less than 500 volt voltage and current, because you to have this, you have to scale down the signal. After obtaining the proper signals in suppose in Sierra, you need to inject it into the low signal interface of the relay via flat ribbon cable, which is a 14-pin ribbon cable, as you see here. And demonstration now. As I have already mentioned, how you have modeled the data and how you get the data in the RTDS and protection relay, and how to model the data to have or perform all these things to be get done. So if I click here, you will see short videos, uh, the signal exchanging, how the relay interlocking is being done. Now it's the red one signal is indicating that overcurrent is activated. Now it is not activated. That means there is no fault in the relay. Again, you will see some blinking lights uh, after some time, maybe. Yeah. Now there is a fault in the relay. That is breaking the breaker. That is open now. Now it will again close.
Vasu,
Okay. Yeah.
we
Yes,
are
sir.
not able to see the video that you are sharing, no?
Okay. Maybe. Maybe I need to share the screen. Maybe. Okay.
Yeah, you can, if you want, you can share the screen. That's it.
Okay. Wait a second. Just sharing it. Stop now. Okay. So is it visible? My screen is visible, right?
Yeah.
Okay. I'm trying to play the video again here. Now it is visible, sir, the video.
Yes, yes. Please go ahead.
Okay. Yeah, that is the data sets we have modeled, and we are integrating relay with the RTDS. And I will explain how it is happening, how we have where we have deployed this relay in order to do so. Yeah, this red indicating that there is fault in the relay and it is tripping the breaker. Now you will see green light. That means fault has been clear and the breaker has been closed again. Yeah, that is the video that I would like to show. Yeah, that is the benchmark network that we have taken. That is the C-gray medium voltage network, and we have deployed this relay here in the feeder at 110 and 20 kV here, and that is the network. Again, as here we have also integrated the SL3350 automation controller. The purpose of integrating this RTEC is to monitor whole distribution systems, voltage, current, and loads profile, active, reactive power, and some distributed energy resources, which is modeled as dynamic PQ source here, PV source, and some battery, and dynamic PQ source, which is a battery here. We are taking all the data in the RTEC to monitor the actual like benchmark distribution system, which is kind of actual to yeah. And that is the second examples, hardware in the loop for data issue detection and dual active redundancy design. After getting the enough confidence while executing the second examples and first example, and we are shifting to testbed development for the example 3, where we have the synchronizing clock SL3350 and SL421 relay, which is acting as a PMU here, and real SL3530 RTEC again, and yeah. That is the simulated network where we take the IEEE 39 bus systems, where we have the PMUs, real hardware that we are integrating also, and the embedded PMU in the RTDS also we are taking. And same way the SL4, like we did in the SL751, we are also injecting the real like simulated voltage and current to the SL421 via low signal interface. The process was same as we did in the while integrating SL751. And RTDS GTNet X2 has two modules, module A and module B, which means that at a time when we simulate, we can take two protocols. We can simulate two protocols in RTDS. For example, here GTNet X2 GSE, which is Goose, means ISC 6150, and module 2, which is GTNet X2 PMU, because I'm also considering PMU, and I'm also taking embedded PMUs from the RTDs. The purpose of this study is that because on the accept cyber attacks, in addition to the cyber attacks, the PMU signals, transferring to the different PDC or data centers, there might be data issue, depending on maybe human error, some configuration error, or some communication latency or communication breakdown. So these things should be detected at the PDC or some controller, because you are aggregating all these signals in a controller and sending it to some data center somewhere. For example, you would like to perform the load setting or some demand response program, or some maybe controlling some other critical assets. So when you do aggregate, conventional aggregations may be happening because, so for example, you have 5 PMUs, number of human counts is 5, right? And suppose you are receiving 50 hertz signal, and that will be 250, right, total. That is the conventional. But if one of the PMU have some issue, then the number of counts will be less, right? You have now only 4 PMU, but you are not considering discount. You need to implement a counting algorithm in such a way that you get the real count. You need to discard the defective one. So your signal should be no total count should be 4 and total should be 200. So that is the purpose of this testbed, is to detect the issue of this PMU data issues, and implementing the dual active redundancy, because I'm taking here 2 SL RTEC, because two was a two RTECs are acting as a PDC, and I have implemented some algorithms in the RTDS, so that these two signals or frequency signals from the RTX, they can be taken to the RTDS, and at a time only one frequency signal from one of the PDC can only be out to the different application. At a time, these two signals cannot be output to the applications, because you need to have some conditioning. For that, I monitor both the message subscriptions from the PDC, and that is done by a algos feature in the IEC 6150, which means that logical node goes subscription supervision, active message subscription supervision. Okay. And the example for, we also working in the hardware in the loop for network microgrids, as we have SLR tags and protection relays, 3 protection relays, and we have automation controllers. The purpose of doing is that this microgrid, network microgrid, the different microgrid, these 3 microgrids can be worked as a cluster during the disconnections from the grid, and can be coordinated when there is one of the microgrid cluster of microgrid may be not getting enough power, then this microgrid has to borrow power from neighbor. So this kind of algorithm we have implemented in our present working testbeds. Our next task will be taking it forward by simulating different cyber threats. That is, here I have mentioned we are working on the attack formulation, and some tools we have implemented, and these tools can perform for false command injection, man in the middle attack, false data injection attack, denial of service, and the protocol can be GOOS or IEEE C37.118, which is PMO protocol. Apart from these protocols, our tools that we have implemented in our lab can be useful for conducting such cyber threats for the DNP, Modbus, and other SCADA protocol as well. And uh, we are still working on this, and hope we can find some good results and share maybe with you. And the example 5, In the example 5, we also working in the initial, conceptual development for the digital twin reference model. As during the course, Dr. Srivastava also told, discussed about the digital twin development and the
No, sir.
Hello.
Sir, Basu sir has some issue with the audio. He's fixing it a bit. I request everyone to be patient. Please, Basu sir is fixing his audio and he will join soon.
hello. Okay. Come. Okay. I think the screen is visible right now.
Yes, sir, it's visible.
I'm sorry, actually, from starting I had some issue with the microphone, and so I joined with another system, but it also got some issue with. So I was talking about the conceptual development in progress about the digital twin reference model. We have developed in our lab here in IIT Jammu. I was talking about the physical grid and digital grid, right? In the physical grid, the real grid we don't have it now, but we take the benchmark Bunsi microgrid, and this microgrid have the three feeder connected to the grid, and one DC battery energy storage systems, combined heat power plant, and solar PV, load circuit breakers and boundary breakers, switches as well. And the same in our the RTDs we have in our RTD lab have the two chassis, one chassis and two chassis. I'm modeling the physical grid in chassis one and modeling the digital grid in the chassis two. My objective here is here the whatever the data I have in the physical grid. Suppose I have the DC power, battery energy storage, control set points, and the combined heat power plant power status, solar PV generation, and maybe the load, active and reactive power, and circuit breaker statuses, and maybe the switching. These data are sent to the controller or energy management systems, where you will have the overall monitoring of the data from the physical grid. This data is going via IEC 6150 and the IEEE C37.1, because I'm also using the PMU, and the whatever data I have in the this controller, that is also sending to the digital grid, where you have the same grid, but the bars will kind of just like in the this actual replica of the Bunsen microgrid that is been modeled in the physical grid. And now at the initial stage, I just implemented whatever happening in the physical grid. Suppose one of the breaker has been tripped, and that also replicate in the digital grid. So that has been implemented. Now our objective is to take all the data coming from the physical grid and compute and send it to another artifact, and where we will compare the values getting from the real physical grid and real grid, and issue some binary signals, so that the algorithm that is tripping the breaker in physical grid can be validated, and if okay, then we can trip the relay in the physical grid, which also should reflected to the digital grid as well. The conceptual that I formulated and learned from this digital twin concept can be available in this YouTube channel, IEEE Task Force on the Digital Twin of Large Scale Power Systems, which is a YouTube channel by the IEEE Task Force, and that is available in this link. In not in shell, what is digital twin? Means you have the physical grid, real grid, and digital version of this, and you are sending this real-time measurement data to your digital virtual grid, and you have data in virtual grid. The data you algorithm, maybe you are implementing some algorithms and computing some and validating it, and this information is sent again to the real grid, because otherwise the this should happen, otherwise the meaning of digital twin is not serve the purpose. But the thing is that when we start thinking about modeling the digital twin from the starting, I means modeling each and everything, it takes maybe it may takes very huge time, long time, maybe it's not possible to implement or model each and every components that is in the physical grid. So thinking might be like this. So my carry forward is that first I was thinking the capacity, like how I can model these things in a short means, in a brief way. I first thinking creating the capacity and grow over time. Whatever I have implemented right now, I have implemented it. But if I want to make it detailed and according to my goal, then it takes time. So I will now grow over the time, little steps that I am taking it now to execute my goal. Whatever I would like to execute by this digital twin reference model testbed. So uh, as I have mentioned, when you are thinking about developing the cyber physical test beds, then someone has to be in his or her mind that what goal you are trying to achieve from the test bed. So that is the concept that we have implemented, and we are thinking to implement it in different way as our goal, and that can be done by by looking at the different perspective and the trends going on, the research and real problems in the industries, what kind of digital twin reference model its demand, or what we can serve for the solutions. Yeah, that is the examples that I have discussed about the cyber physical test beds. Now, as I have mentioned in the chronology of the presentations, that I would like to share the some experience in the transmission system modeling, which is Northern Regional Power Grid, which consists of 246 buses, 42 synchronous generating stations, which consists of total 60 generators. The database data I'm taken from that is from the IIT Kanpur here. The source is from IIT Kanpur, and there is one lab, PS lab. The data is taken from there. The aspects, the aspects of simulation is the purpose assessing the performance of the utility scale battery energy storage systems for primary frequency response. The scope is active power control from the battery only, not reactive power. The test system and simulation tool. The test system is Northern Regional Power Grid up to 220 kV and 400 kV level, and which is model and PSSC software. And the cell engine. The data for the NRPC grid is available, but this .saf file and .sld single line diagram and other dynamic file regarding the generators, excitation systems, and turbine governors, which is not available. So, but data, what data and the kind of generations we have has some governor excitation systems. Data is available online. So based on that, we have categorize this in different sections. Suppose generating station generating at a less than 250 MVA and greater than equal to 250 MVA. This type total 4 types has been created, and all the hydros, which is a Jensen model, and excitation SCRX, and that is the hydro governors, and that is for the thermals governors and excitation systems. Those who are familiar with the PA system might understand this one. If somebody having some doubts or not understanding this, maybe we can discuss, or if you have query, please you can ask in the answer and questions. The placement of solar PV and wind turbine in the northern regional grid. As I mentioned, that the actual purpose of the starting this one is to place the utility scale battery energy storage systems with high, renewable energy integrations. This integration is the performed, by looking at the guidelines published by the Indian Smart Grid Forum. Northern Indian states such as Rajasthan, Uttar Pradesh, Punjab, and Delhi are the major hotspot for the solar. And the wind, Rajasthan is the most favorable among the northern states. Therefore, the simulation for future scenarios with sum of total 5,800 megawatt renewable from the solar and the wind has been integrated, with accounts like total of 30.62%. And deployment of BESS, utility scale battery energy storage systems in northern regional power grid. The locations where I should deploy is already mentioned in the Indian Smart Grid Forum roadmap for India from 2019 to 2032. The location of BES is deployed along with the bus of maximum RPZ. RPZ means renewable generating plant penetrations, except in the states where renewable generating plant potential is low, but hydropower potential is high. The location of BES states. In the interconnection requirements from the Indian Electricity Grid Code says that battery utility scale battery should be connected to the 33 kV and should be enabled with a governor group of 5% to provide a primary frequency response during over and under frequency conditions with maximum frequency deadband of plus minus 36 millihertz. And that is the formula that we have used to coordinate or share the power from different battery energy storage units. And there is the table which says the different configurations and the that we have adopted during the simulations for down and up regulations and different frequency dead bands in the battery energy storage systems for up and down regulation is displayed in the table. And that is the single line diagram of northern regional power grid and renewable generating plants location. On the right here, I am pointing my cursor location of RPGs. Means suppose in Delhi, as mentioned in the report, it should be in the 18 bus. Uh, and for Haryana, this location has been already mentioned in the report. And different colors, the different indications represents already. Yeah, I have illustrated in the note section here, and it is a single line diagram. Total of 246 buses and the 42 generating stations and total of 60 generators and megawatts RPGs deployment in RPG for different states. Different capacity of renewables from the solar, wind, and battery has been deployed during our study. That is the forecasting and simulation case studies. The simulation scenario is created as per the forecasting of the solar, wind, and according to the load profile and frequency profile for the day. Here on the left, forecasted RE and NRPG, which is taken from the Northern Load Dispatch Center. I have taken this data on the 30/06/2023, and this curve represents the forecasted solar, forecasted wind, and load conditions during that day. And at the bottom, there is a frequency profile recorded and available online. I just take a screenshot, but sorry, I have to mention here the reference, but I forgot. I'm sorry. And based on these scenarios here, this highlighted in the green and this color, according to that, I have created a simulation. The contingency that I have created, sequence of events for first at 1.5 seconds load at Moga 2 has been tripped because this 1.5 second represents here that is the moment when there is solar power is coming online in the grid. And similarly, I have also tripped the load in the Jalandhar trip, and these loads are disconnected during when there is a solar peak and wind power is going down and load also going down. And again, when there is load is picking off and wind power is coming in, but solar is going down. Load is coming in again means we are connecting again whatever we have disconnected loads earlier. And also some line trip has been done because of immediate just to show the frequency is going up. We have tripped some lines, transmission lines, which leads to cascading faults, and that is leading to thermal power trip and solar hydropower trips. That is all the scenarios that we have created in order to show different frequency events frequency disturbance uh, to to check whether battery is performing well as per we design. And that is the results that we have getting from the simulations. Suppose battery deploy in the Delhi, Haryana, Himachal and Jammu, Punjab, Rajasthan and Uttar Pradesh. These are the response from the battery during the down frequency and up frequency event. During the down frequency event, battery was releasing the power, which is showing in the negative. uh, Releasing the power means compensating the power, whatever compensating the power. Suppose load has been 3 when frequency was high. So in this time, sorry, absorbing the power, charging the battery. Okay, sorry. And when there is a frequency down, then battery has to discharge, right? In the scenario 2. That is exactly what we wanted. It's working fine. And that is the performance from the battery charging and discharging here. And the frequency during when there was frequency event for the up frequency event, that is one. This blue line represents without the battery energy storage systems, and red one is with the battery energy storage systems that deploy at the different locations, as we say improvement in the frequency response. And that is the response from the wind turbine and solar that we simulated here. Yeah. And the simulation results and analysis. Now we would like to compare the response from the battery, thermal and hydro in terms of RAM rate. On the right, that is the RAM rate response from battery deployed in the Delhi, for example, Uric Hydro Jammu and Kashmir, and Oriya Thermal in Uttar Pradesh. The RAM rate is calculated according to this formula, and I have tabulated here for the snapshot for better understanding. For utility scale battery energy storage systems deployed in the Delhi, for scenario 1, that is battery was charging, right? During that incident, battery was charging at a rate of 36 megahertz per second. And at the same moment, this thermal was only how much? 21.07 megawatt per second, and the hydro was performing 24.423 megahertz per second. In the scenario 2, when there was frequency event, for the time battery was discharging the power to compensate sudden load increment, and that time battery was releasing 53 megawatt per second, and the thermal was providing only 21.50, and the Salal hydropower plant was giving 39.92 megahertz per second. If you see from the table, the best performance given by for the the power compensation is coming from the battery energy storage systems, which prove that battery has enough potential for you know tackle with the frequency events whenever we have more renewables in the grid. That is the message that I would like to convey with you. And that was my findings, some experience, and in terms of cyber physical systems and simulation experience in our other lab. So thank you everyone for listening to me, and I'm very sorry for technical glitch in between the presentation. At the last, I would like to thank you, Dr. Arnav Sukla, my PhD advisor, for giving me opportunity to present my findings and experience. And I was very happy. I get very happy to share with my experience with my research fellow mates and participants. Thanks a lot again. Thank you, sir. Uh, Maybe a participant can ask questions if somebody have some questions to ask. Okay, I will be checking the slide. Okay, the physical grid once micro search is one. It is a complete hardware-based test setup. Mean the entire three bus system is hardware, or it is built in RTDs. Okay, I will answer this one. First, I would like to show the presentation so that we can have the good visualizations on. Yeah. Okay. This Bansi microgrid, it's already there in the RTDS, and this microgrid model in the RTDS, it's the real life microgrid that is available in USA. USA, that is the test bed. I have considered this as a real physical grid, because that is the real microgrid available in the real life example of microgrid available in the US. So that's why that is the benchmark, right? So I have considered this as a physical grid, and in this grid I have the physical relays, this SL 421 relays, and active is acting as both overcurrent protection relay as well as the PMU, and the I have the SL751 A and SL751 protection 51 protection PIDA protection relays that I have deployed in the three Peter. Maybe I can show you a bit in the RTDS also, so that you can have the good understanding on it. I think these figures, the slide is visible. Okay. Yeah. The grid I was talking about, Bansi microgrid. Here you see, that is the grid, right? And I have feeder 1, feeder 2, and feeder 3. Here, this feeder 1, feeder 2, and feeder 3, I'm having the actual as the SCL relays for feeder for overcurrent protection. And all these data, suppose load, battery energy, resistance, breaker status is grid power, and the load, active and reactive power, solar PV, and some the critical parameters has been taken to the RTEC, this controller, and the same has been transferred to the again another digital replica of the physical grid that we have model in board in chassis 1 and chassis 2. Yeah, I think I may have clear your doubt or not. Yeah, you can just take your microphone and I think ask directly. Say that.
Yeah, yeah, yeah. I understood it. Yeah.
Okay.
Okay. So the relay and the these parts are like kind of physically modeled or physical things. That's all the
Yes.
things that you have kept in the model. I
Yeah.
get it. Get it. Get it. I got it. Yeah.
Yeah, this is the physical thing we have incorporated in the feeder, right? As I have shown you 3 feeder, and there is a breaker here. This breaker has been, 3 bio protection relays that we have integrated in the RTDS. That is the actual hardware. Okay. Is there more questions from the participants? Okay. I think, yeah, we are on the right time. Sir, uh, my presentation is over right now, so can we put the link of the quiz here in the search section?
So you are not audible.
Sorry, I'm really sorry. So, Professor Anurag Srivastava sir is also here. What we can do, Professor, if with your permission, what are we are planning? We are planning to have a small, small quiz on the subject that we have conducted from last 10 days, and